This is lesson 6.1a. In lesson 6.1a, we're going to start out by talking about the rules for exponents. So we have our foldable here. The first rule that we're going to talk about is the product of powers. Remember that product means multiplication. So when multiplying exponents with the same base, so the x here is the base, or the 4 here is the base. So when you have the same base, you keep the base and add the powers, or you add the exponents. Okay. So if we're looking at it, if we have x to the nth power times x to the m power, then that means that we have x to the m plus n. It's a little bit difficult to see that plus sign in there, so we're going to write over top of it. Plus. If I have 4 to the second power times 4 to the fourth power, it becomes 4 to the sixth power. And the reason for that is because I'm going to use blue for this one. So 4 to the second power means 4 times 4. And 4 to the fourth power means 4 times 4 times 4 times 4. And because we're multiplying these two sets, I'm going to put that multiplication symbol in between. If you counted the amount of 4s we're multiplying, we have 1, 2, 3, 4, 5, 6, which is where 4 to the sixth power comes from. Because remember, exponents tell you how many times you're multiplying the base, and the base is 4. So I'm multiplying the 4 6 times. For our second rule, we're going to talk about the quotient of powers. And the quotient of powers says when dividing exponents, because remember quotient means division, the answer to division. When dividing exponents with the same base, again, keep the base, and this time we subtract the exponents. So if I'm looking at, when I'm looking at these, so I have the x to the nth over x to the m, and if I were to rewrite it, it would be x to the n minus m. So my base is x, n minus m. And down here we have 4 to the 9th over 4 to the 6th. So we had 9 minus 6 is 3. And the reason that this works is that we have fractions for this one, okay? So I'm going to draw my fraction bar here. And on the top, I have 4 to the 9th power. So I have 9 fours being multiplied. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We're out of space, so I'm going to just stack them up there. So I have 9 fours being multiplied on the top. On the bottom, 4 to the 6th, I have 6 fours being multiplied. 5, 6. And when we do this, if you think about being able to reduce fractions, right? We think about how many times can I reduce the top and the bottom by the same number? Well, here, I'm going to be canceling all the ones that have a partner. So if I look, these 4s make a pair. They create 1. 4 divided by 4 creates 1 here. It creates 1 here. And 1 here, and 1 here, and 1 here. What do I have left over? I have 3 4s being left over on the top, and I'm multiplying them. So I have 4 times 4 times 4, 4 to the third power, and it's on the top. So it's like saying 4 times 4 times 4 over 1 whole is left over. So 4 to the third power is my most simplified answer. For power of a power, we are raising a power to a power. In this instance, we're going to multiply our exponents. So I have 4 to the second raised to the sixth power. So it's kind of like when you do the distributive property and you multiply. So 4 to the second times 4 to the sixth is 4 to the 2 times 6. So 2 on the inside, 2 times 6 is where we get 4 to the 12th. Now for the 0 exponent, any number raised to the power or to the 0 power is equal to 1. It doesn't matter what the base is. If it's raised to the power of 0, then the answer is 1. So for example, I could even have something like 4, well, let's use a different number. Let's do 3.67 to the power of 0. It's still equal to 1. So it doesn't matter what the base is. If it's raised to the power of 0, it's equal to 1. This is the stuff that tricks people up often though, because of the variable. If a variable is raised to the power of 0, it is still 1. And for our negative exponent, a negative exponent causes the number to be rewritten as the reciprocal of the original number, and the exponent becomes positive. So you can't really see it too well right here. So here's x to the negative nth power. So we make this the reciprocal. So this is like x over 1, right? So I flip it to become 1 over x, and that n, which was our exponent, becomes the exponent at the bottom of the fraction. 4 to the negative 6th power. We've got technically 4 over 1 to begin with. We flip, we've got 1 over 4, that's reciprocal. And to the 6th power. You could simplify that. You could figure out what 4 times 4 times 4 times 4 times 4 times 4 is and write it as 1 over that number. That's fine. Sometimes they're just asking you to write it as the reciprocal with the power at the bottom. One thing that I like to tell people as a reminder, so I like to remind people that the negative in the exponent becomes like the fraction bar. And so that makes us have to make that fraction. It's just that little reminder that, hey, this fraction bar is a result of that negative in your exponent. So make sure that you will have a fraction for your final answer. This is lesson 6.1b. In lesson 6.1b, we're going to continue to talk about exponent rules. A couple additional rules we want to talk about are the power of a product rule. In power of a product, each base is raised to the power and then you multiply. So for example, if I have x times y inside parentheses raised to the power m, then I would basically kind of like distributing. So m gets distributed to x as well as the y. So I have x to the m power times y to the m power. This one we have 4 times 5, and the whole set of parentheses is raised to the 6th power. So that's like saying 4 to the 6th power times 5 to the 6th power. We also have power of a quotient. And in power of a quotient, the numerator and the denominator of the base are raised to the power, and then you divide. So for example, if I have 3 halves raised to the 5th power, it's really like 3 to the 5th over 2 to the 5th. So I could find what 3 to the 5th is and then divide it by 2 to the 5th and get either a simplified fraction or perhaps a whole number, or in some instances a decimal. This one we have a over b raised to the m power. So it's the same as a to the m over b to the m. So let's see how we can apply these two rules in a couple of examples. So for example 1, the first problem that I'm going to look at, we'll call it problem A, is 3d over 2 raised to the 4th power. So if we think about our power of a quotient, then the numerator and denominator get the fourth power. But also, if we're looking at, so let's do that real quick. So we have 3d. That whole thing is raised to the fourth power over 2 to the fourth power. Now thinking about power of a product, this would be 3 to the fourth power times d to the fourth power. So we've got 3 to the fourth times d to the fourth over still 2 to the fourth power. So if we're going to simplify this a little bit, 3 to the fourth power is 81, and d to the fourth cannot be simplified, over 2 to the fourth power, which is 16. So our final answer for this one is 81d to the fourth over 16. Now let's take a look and see what it would look like if we had a negative exponent. So let's do 2x over 3 raised to the negative fifth power. So when I'm looking at this, remember it's like distributing this exponent to the top and the bottom of the numerator and denominator. So I have 2x to the negative 5 over 3 to the negative 5. So just like we've done in the past, let's take the top and make it a fraction, and then the bottom make it a fraction. But we're going to use this fraction bar as our old version of the division symbol. So I've got 1 over 2x to the fifth. That takes care of my negative in my exponent. Divided by, so that takes care of the fraction bar, 1 over 3 to the fifth. So to simplify, this is 1 over 2 to the fifth times x to the fifth, divided by 1 over 3 to the fifth. So if we keep change flip, because we're dealing with division of fractions, then we have 1 over 2 to the fifth, x to the fifth, times 3 to the fifth over 1. And when we multiply, that gives us 3 to the fifth over 2 to the fifth, x to the fifth. Well, 3 to the fifth power is 243, and 2 to the fifth is 32. X to the fifth stays x to the fifth. Now, another way that you could have written this, if you look at how we started and we look at this step here, this could also have been, if you want to eliminate your negative in your exponent, you can take a reciprocal of the whole fraction. So we could have done 3 over 2x and raised that all to the fifth power. So then that would have given us this, what we have down here, which is 3 to the fifth, 2 to the fifth, x to the fifth. So if I have a negative exponent, I can take the reciprocal, which takes care of the negative in your exponent, and then raise all of the parts to whatever power you have in this instance, 5. For example 2, we're going to look at a more complex question. So we have 3m to the negative fifth, n squared, over 4m to the negative 2, n to the 0, and this is all raised to the second power, times m times n to the fourth, over 9n, and this all raised to the second power. So we need to take these piece by piece, all right? What we have here is 3, so everything gets this squared, so 3 squared m. And remember, our power to a power we multiply, so negative 5 times 2 is negative 10. N, 2 times 2 is 4, over 4 squared. M, negative 2 times 2 is negative 4. And we have n to the 0. Well, 0 times 2 is still 0, so this is still n to the 0. Times m squared. N, 4 times 2 is 8. 9 squared. N squared. Over here, because we've got some negative exponents, we're going to kind of clean up. We're going to take it just like we've done before, the top over the bottom, so they're separate parts still. So 3 squared is 9. M is going to be 1 over m to the 10th times n to the fourth over 1. And then we have 4 squared, which is 16, times 1 over m to the fourth, because that fourth is to the negative, times 1 whole. All right, and we haven't changed much over here. So we've got m squared, n to the 8th, over 81, n squared. So if we clean this up, on the top we have n, 9 times n to the fourth is 9n to the fourth, over m to the 10th. And again, we're using this fraction bar as a division symbol. And on the bottom we have 16 times 1 is 16, over m to the fourth. Nothing has changed on the right side yet, so we're just going to rewrite this. Here we're going to keep change flip, so we have 9 n to the fourth over m to the 10th times, flip our fraction, m to the fourth over 16. Nothing over here has changed yet, so m squared n to the 8th over 81 n squared. All right, so if we multiply straight across, we have 9 n to the fourth, m to the fourth, over, now I can write m to the 10th times 16, but I'm going to write 16 times m to the 10th, because then it gets my whole numbers over here together kind of matched up, and then the m's are closer to one another so we can see for canceling, times m squared n to the 8th over 81 n squared. So we need to think back to our properties with our division, and when we have things that match, then we can do some canceling. Okay, so for example, here 9 and 16, I can't cancel anything with those because they don't have any common denominator or common factors, but if they did, I could do some reducing as if they were a fraction on their own. And n does not have any matches on the bottom, so I'm just going to leave that as n to the fourth. But if we look here, we have m to the fourth and m to the 10th. And if we think about it, there's 4 m's on the top and 10 m's on the bottom. So 4 of the m's on the bottom will cancel, leaving us with 6 m's. So m to the 6th now. Here we only have m's on the top, m squared. We only have 81 as our whole number, but our n's, we have n to the 8th on the top and n to the 2nd on the bottom. So there's 8 n's at the top, 2 on the bottom, which if we cancel, leave us with 6 n's on the top. So we need to multiply straight across. I'm going to kind of draw an arrow up here to give us a little bit more room. And we have 9 times no other whole number on the top. We have m squared, that's the only m. and n to the fourth times n to the sixth. And remember, if you're multiplying, we're going to be adding the exponents. So that leaves us with n to the 10th. And then I've got 16 times 81. We'll just write that for this point here, 81. And then we have m to the 6th. I'm going to simplify this up a little bit. I have 9 n to the 10th. Now look here, we have m squared and m to the 6th. So I have 6 on the bottom and 2 on the top. That leaves us with 4 m's on the bottom. I only have n to the 10th at the top, no other letters left up there. Down here we have 16 times 81, which is 1,296. But 9 goes into 9 as well as 1,296. So 9 goes into 9 one whole time. So I have n to the 10th left at the top. It goes into 1,296 144 times. And I still have my m to the 4th down here. Now for our last example, example 3. A jellyfish emits about 1.25 times 10 to the 8th particles of light or photons in 6.25 times 10 to the negative 4 seconds. How many photons does a jellyfish emit each second? So we're talking about scientific notation here. I'm trying to divide these particles by these seconds. So I have 1.25 times 10 to the 8th over 6.25 times 10 to the negative 4. So right now I'm going to use the x's multiplication, but so that we don't think that it is a variable, in the next step I'm going to use just the regular multiplication symbol, the dot for multiplication. So I'm going to take these part by part. So these are similar bases because they're just numbers with a decimal. And then these have a base of 10. So I'm going to kind of separate them into their own bases and their own fractions. So I have 1.25 divided by 6.25 times 10 to the 8th divided by 10 to the negative 4. So when I do 1.25 divided by 6.25, I get 0.2 times, now remember, I keep the base, 10, and I subtract the exponents. But remember, when you subtract 8 minus negative 4, it's the same as saying 8 plus 4. So my exponent on this 10 is going to be a 12. So I have 0.2 times 10 to the 12th. Now, flashing back to scientific notation, the number before the base 10 has to be greater than or equal to 1, but less than 10. So I need to move my decimal point 1 time to the right to make it a whole number of 2. But when I do that, I'm taking away a place value of 10. So I'm taking away 1 whole 10 from my power. So I'm actually going to now have 10 to the 11th power. If I had to move it to the left, let's say I had 12 and I had to make, I had 12 and I had to make it 1.2, then I would have moved it to left and I would have added to the exponent. So if I move to the right, I subtract 1 from the exponent or however many times you move it. And if I'm going left, I'm going to add to the exponent. So it would be 2 times 10 to the 11th photons emitted each second. This is lesson 6.2. In lesson 6.2, we're going to start talking about roots. So one thing we need to look at are the rules. So real nth root of a. So it says let n be an integer greater than 1 and let a be a real number. And so here we've got some rules that we're going to have to follow for this. So if n is odd, then a has one real nth root. So the nth root of a equals a to the 1 over n. If n is even and a is greater than 0, then a has two real nth roots. And that's positive and negative. That's what that plus over minus means, positive and negative. Nth root of a, it also equals positive or negative a to the 1 over n power. If n is even and a equals 0, then a has one real nth root, which is the nth root of 0 equals 0. So if you think about it, 0 times itself is going to continue to give us 0. If n is even and a is less than 0, then a has no real nth roots. And the reason for that is because if we multiply two negatives together, we cannot get a negative answer. So if a is less than 0, it's saying that the answer to multiplying an even number of times with negatives would give you a negative, and that's not possible. So that's why there's no real nth root. And in future courses that you take, you're going to talk about imaginary numbers, which there are some possibilities with imaginary numbers in this. We're not going to be dealing with that yet. So let's take a look at these rules. For example 1, we're going to look at two different things. So the first one, we'll just call this a. And we're going to say that n equals 6 and a equals 64. So if we use the format that we have, which remember was the nth root of a, then n, or 6, is going to be right here. So it's actually the 6th root of a. And in this case, a is 64. So this goes underneath that, what you know it as is the square root symbol. It's really a root because it could be a square root and this would be like a 2. It could be a cubed root, this would be a 3. This is a 6th root. So the 6th root of 64. So another way to write this is it could be positive or negative for our answer since this is even. And we could write it as 64 to the 1/6 power. So 64 to the 1/6 power. And if we simplify this, 64 to the 1/6 power is positive 2 or negative 2. So it could be either one. You'll write as plus minus 2. Sometimes if they give you two different boxes to enter answers or something like that, you'll write 2 and then the other one you'll write negative 2. So there are two possible options. For example 1b, we're going to look at if n is 3 and a is negative 27. So again, n represents what root we're dealing with. So we're dealing with the cubed root, or 3, and a is negative 27. So if we were doing an even root, let's say we're doing a 4th root or a square root even, we wouldn't have had an answer. We would have had no real root because it's saying that this is equal to negative 27. So the only way we can possibly get an answer is because we are dealing with an odd number for the root. And what that looks like is in parentheses, negative 27 to the 1/3 power. And if you take negative 27 to the 1/3 power, we're going to get negative 3. Because negative 3 times negative 3 is positive 9. Positive 9 times negative 3 gives us that negative 27. For example 2, we're going to look at a couple different ways to write these things. So if I have the negative cube root of positive 8, What this means is that, see how the negative sign is outside of the root? It's kind of like in the past where we had a negative outside of parentheses. So we had like -1 times our answer. Similar idea here. So it's the same thing as -1 times the cube root of 8. And if you think about it, we could do 3 2's to get 8. So it'd be like 2 times 2 times 2. So therefore, the cube root of 8 is 2. And we've got this negative symbol outside. So really our answer for this is -2 because it's the opposite. That's what this means, the opposite of the cube root of 8. Well, the cube root of 8 is 2. The opposite of that is -2 for our final. For part B, we have just the cubed root of -8. So what this one is looking at is that negative sign is underneath. So the factors that we're dealing with to make -8 are going to be negative. So we have, it would be like the cubed root. And again, we know 2 times 2 times 2 will give us 8. So this one would be like -2 times -2 times -2. So notice the difference here. This 8 is negative, this one was positive. Look at our 2's that we have here. These ones are negative, these ones are positive. But the cubed root of -8 is still -2. So these two produce the same answer, but for different reasons. And then for part C, we have -16 to the 1/4 power. Because this is an even power, right? It's like saying the 4th root of -16. Because the negative is under this radical symbol and this is an even number, we would have to say no real solution for this one. We can't have an even number of negatives being multiplied and end up with a negative answer. All right, so we're going to look at another set of rules we have on here. This next set is for rational exponents. So, for example, like fractional exponents. So let a to the 1 over n be an nth root of a, and let m be a positive integer. So if we're looking at these, it's saying a to the m over n equals a to the 1 over n, the denominator, times m. So if you think about our product of powers, or sorry, our power to a power, we have the fraction times this power. So we multiplied them. Therefore, we got, they kind of sectioned it off into this whole thing as they kind of like work backwards. So this is the simplified version. This is what it looked like when we have power to a power initially. So that we're used to seeing it here and going to there, where we can also take it and work backwards and reorganize it. But another way to write it, since we have our fraction inside, remember that denominator can be your root, so to the nth root, and then the power outside is still the same. So if we look at it in terms of actual numbers, let's take a look at example 3, and we have 256 to the 3/4 power. So one way that we can write this, if we think about it as a is our 256, so that's still our base, 256, and I can take the denominator 4, and I make it to the 1/4 power, and then I raise that to the 3rd power because I have 3 sets of that 1/4 power. That's what this means. 3/4 is 3 sets of 1/4. Another way that I could write it, if I were writing in terms of radicals, because sometimes you'll be asked to write it as a radical, I could write it as the 4th root of 256 to the 3rd power. So putting that 2nd power underneath the radical, and it's the 4th root of 256 to the 3rd power. Or I could write it as the 4th root of 256, and then the answer to the 3rd power. So those 3 different ways, but they all get us to the same conclusion. And what that is, would be, if I take 256 to the 4th power, I get 4. And then I raise that 4 to this 3rd power that we haven't used yet. 4 to the 3rd power is 64. And you'll get the same answer for all these. So if you take 256 to the 3rd power, take the 4th root of that, you get 64. The 4th root of 256, raise it to the 3rd power, you get 64. Example 4, we're going to be using some of these rules and applying them to more real world scenarios. So the radius r of a sphere is given by the equation r equals 3v over 4 pi, all raised to the 3rd power, where v is the volume of the sphere. We're going to find the radius of the beach ball to the nearest foot, and we're going to use 3.14 for pi. So down here, we're going to see that I have a volume of 113 cubic feet. So I have to take this initial equation, r equals 3 times the volume. Our volume is 113, so we're going to use that. We're going to put it over 4 times pi. Notice they asked us to use 3.14 for pi. And then I'm going to raise all of this to the 1/3 power. So when I simplify, I have 3 times 113 is 337. 4 times 3.14 is 12.56. I'm going to raise this to the 1/3 power still. And if I raise this to the 1/3 power, or in other words, if I take the cubed root of this fraction, 337 over 12.56, then I get r equals 2.99964, ... It keeps going. But they want us to round it to the nearest foot. So if I look at that, this 9 is going to make my 2 become a 3. So the radius for this is approximately, I'm going to use my squiggles here, approximately 3 feet. And example 5, to calculate inflation rate, the annual inflation rate, in decimal form of an item that increases in value from p to f, so present to future, over a period of n years, you can use the equation r equals f over p to the 1 over n power minus 1. So we're going to find the annual inflation rate of a house that increases in value from $200,000 to $235,000 over a period of 5 years. And then we're going to round our answer to the nearest 1/10 of a percent. So for example 5, we have our equation, r, or our rate equals future over present raised to the 1 over n power, answer minus 1. So when I'm looking at this, according to my question, my future price is $235,000. So that's going to be 235 on the top, 235,000 I should say, over my original price, or my present price, $200,000. This is raised to the 1 over, and n, if we look at it, n stands for years, and it's 5 years for this one. So 1 over 5, or 1/5 power. And then we have to bring down that minus 1 because we haven't done anything different with that. So if I do 235,000 divided by 200,000, I get 1.175, still raised to the 1/5 power, minus 1. And if I do 1.175 to the 1/5 power, or in other words, the 5th root of that, the same thing, then I get and then subtracting 1, I get 0.03277, etc. So if I'm looking at this in terms of a percentage rate, remember that I have to look at, I would move the decimal place 2 times because it's a percent out of 100. So I have to look at, if I move it, we've got 1, 2. So this is approximately 3.277, etc. And they're asking us, let's take a look. They're asking us to round it to the nearest 1/10 of a percent. So if I'm looking at 1/10 of a percent, I'm looking here, and I have 7 makes this 2 become a 3. So my rate is approximately 3.3% inflation over those 5 years from our original price of $200,000 to $235,000. This is lesson 9.18, and this lesson we're going to be talking about radical expressions. So a radical expression is an expression that contains a radical. So remember those radical signs look like the square root signs, things like that. Simplest form when we're talking about radical expressions is when the following 3 conditions are met. No radicands have perfect nth powers as factors other than 1. No radicands contain fractions, and no radicals appear in the denominator of a fraction. So in order for us to have simplest form, we have to make sure that all of those things are taken care of. So some of the ways that we can take care of those are to use these 2 properties. So we've got the product property of square roots. And in this, it says that the square root of a product equals the product of the square roots of the factors. So for example, if I have the square root of 9 times 5, it's the same thing as the square root of 9 times the square root of 5. That's helpful to us because we know that 9 is a perfect square and the square root of 9 is 3. So 3 times the square root of 5 would be the simplified answer for that one. For the quotient property of square roots, it says the square root of a quotient equals the quotient of the square roots of the numerator and denominator. So what that is talking about is if you have the square root of 3/4, for example, it's the same thing as the square root of 3 over the square root of 4. Now again, this is helpful to us because in this one, 4 is a perfect square. So in order to simplify this just a little bit more, the square root of 3 can't be simplified, so we leave that the way it is. But the square root of 4 is 2. So square root of 3 over 2 would be the simplified version for that one. So let's take a look at example 1a. So we're going to be simplifying the expressions in this. Just like we were seeing in the examples above, we are going to be looking for perfect squares when we're doing our simplifying. Because if I can find a perfect square, it's going to help me to find the rest of the pieces that I'm trying to do. So for letter A, we have the square root of 108. So what I'm thinking about is I know that I can divide 108 by 3, and I will get 36 and 3 for my factors. So if I'm simplifying this, I would have the square root of 36 times 3. Now, if I don't know that right off the bat, can I try other options? Absolutely. Look for those factors that you can multiply to create 108. And if you notice a perfect square in those factors, those are what we should be working with so that we can simplify this as far as possible. So once I do the square root of 36 times 3, I know that this is the same thing as the square root of 36 times the square root of 3. The square root of 36 is 6. So our final answer for this one is 6 times the square root of 3. That's as simple as we can get for that one. For example, 1b, we have the square root of 9x cubed. Okay. Well, I'm noticing right away that 9 is a perfect square. The other thing I think about with my variable here, with it being to the 3rd power, I'm like, okay, well, I remember my exponent rules, and I know that if I had x squared times x, I could get x to the 3rd power. So let's expand it using that information. So we have 9 times x squared times x. So we're basically undoing this cube right here. The reason I'm doing that is because now I realize we've got the square root of 9 times the square root of x squared times the square root of x. Well, the square root of 9 is 3. The square root of x squared is x. And then I'm multiplying it by this remaining square root of x. So if I knew what x was, I'd be able to simplify it farther. But at the moment, that's as simple as we can go. All right, so let's take a look now at some of the questions from example 2. We're going to be focusing more on our quotient property for these ones. So example 2, let's slide this up a little bit. In example 2a, we have the square root of 15 over 64. So when I'm looking at this, I remembered that I can do the square root of 15 over the square root of 64. 15 is not a perfect square, but 64 is. So I know that the square root of 15 is going to stay, and then the square root of 64 is 8. So our final answer for this one is the square root of 15 over 8. All right, so for letter B, we have the square root of 81 over x squared. So now I remember, okay, 81 is a perfect square. So I've got square root of 81 over the square root of x squared. They both look like perfect squares, so there's nothing I really have to expand inside of those radicals. And then I know that the square root of 81 is 9, and the square root of x squared is x. Now again, if I don't remember what my perfect squares are, or I don't remember what the square root of these numbers would equal, it is absolutely okay to double check those using your calculator. Just remember that we want to put the square root answer into those places. All right, so the next thing that we want to talk about is that we can also extend the idea of the product and quotient properties for square roots to other radicals. So we can also use them for cube roots, which is what we're going to talk about now. And when we're using these properties for cube roots, remember that the radicands can contain negative numbers. Because remember, when we're talking about cubes, if I'm multiplying 3 negative numbers, a negative times a negative is a positive, times that 3rd negative gives me a negative answer. So if I get something that ends up being a negative under the cubed root, it's going to be okay because I can actually expand that into an answer that will make sense. All right, so letter A, we have, example 3, letter A. we've got the cubed root, that little 3 floating right there, that's what stands for cubed root, of negative 128. All right, so for this one, if I'm just looking at it, I'm like, well, the first factor I might try is, okay, 2. Well, if I did 128 divided by 2, I would get 64. Well, 64 is a perfect square, so I'm going to use that when I'm simplifying this one. So we've got the cubed root of negative 64 times 2. When we simplify this a little bit further, we know that we have the cubed root of negative 64 times the cubed root of 2. Well, the cubed root, or sorry, 64 is a perfect cube. I think I said perfect square earlier, but it's a perfect cube as well, because if I did 4 times 4 times 4, I'm going to get 64. So this is going to be negative 4, because remember, negative times a negative times a negative will give me that negative I'm looking for right here. So negative 4, and then this is not a perfect cube for me, so I'm just going to keep that the way it was. So times the cubed root of 2. So negative 4 times the cubed root of 2 is going to be our final answer for this one. Purple for grimace. All right, so we've got letter B. For letter B, our expression that we're going to simplify is the cubed root of 125 x to the 7th. So I know that 5 times 5 times 5 is 125. So I realized right away that, okay, 125 is a perfect cube, because that's what I'm looking for now. Before I was looking for perfect squares, now I'm looking for perfect cubes. And if I look at x to the 7th, I can expand this into, let's write this down real quick, cubed root of 125 times x to the 6th times x. And now I'm sure some of you are probably thinking, Mrs. Weber, how do you know it's x to the 6th power? Well, if we think back to our rules about exponents, right? We had x to the 3rd times x to the 3rd. I would keep the base and add the exponents. Well, 3 plus 3 is going to give me x to the 6th power. So if I'm trying to take a cubed root, I'm trying to think about what I could multiply to, or sorry, not the 3. It's a cube, Mrs. Weber. We're going to the 2nd power. Sorry, that's so confusing for you. So we're going to have to the 2nd power. It's a cubed root. My mind's still on my square root. So it's 2 plus 2 plus 2. So 2 plus 2 plus 2. That's how we get our 6. Because I have those 3 multiplied, but when I multiply, I keep the same base and I add the exponents. So x to the 6th is why we're using that for this one. All right, so then we have the cubed root of 125 is 5. The cubed root of x to the 6th power is x squared, right? Because that's back to where we were here, that x squared. And then we have just this cubed root of x, because we didn't use that one yet. It's not a perfect cube, so that's still there. So 5x squared times the cubed root of x will be your final answer for that one. Letter C, we have the cubed root of y over 216. So this is one I didn't notice right away because I'm not as good with my perfect cubes as I am with my perfect squares, but 216 does happen to be a perfect cube. And again, you can double check these when you get to the different problems that you're working on. But this is going to give us the cubed root of y over the cubed root of 216. So just like we did when we were squaring our things, we have the cubed root that can be split up in our fraction as well. So this is going to give us the cubed root of y over the cubed root of 216 is 6. So the cubed root of y over 6 is your final answer for C. And letter D. This one has a lot of parts to it. So for letter D, we have the cubed root of 8x to the 4th over 27y to the 3rd. All right, so I'm starting to think about, okay, what are my perfect cubes for this one? I actually do know that 8 is a perfect cube and 27 are a perfect cube. But now I need to think about, okay, what can I expand in my exponents so that for my variables so that I can make those simplify as much as possible. So we've got the cubed root of 8 times, now if I did x to the 3rd power, that's a cube, and then I would still have 1x left over. So x to the 3rd times x, that's the top. 27, cubed root of 27. And y to the 3rd is also a perfect cube for us here, so that's helpful. Don't have to expand that one at all. All right, so we have the cubed root of 8 times the cubed root of x cubed times the cubed root of x over the cubed root of 27 times the cubed root of y cubed. All right, so we're going to simplify from here. The cubed root of, let's set this over a little bit. Cubed root of 8 is 2. The cubed root of x cubed is x times the cubed root of the other x over cubed root of 27 is 3. And the cubed root of y cubed is y. So 2x times this cubed root of x over 3y is the most simplified version for that question.